Um, I'm very excited to be talking to you all about some of these advances we made in the area of magnetic resonance fingerprinting. I must also mention that the work that I'm going to show you today, the PhD student, Enlin Chan, incidentally, he's going to be defending in the next few hours. So it's all coming together nicely that we're talking about his work and he's going to be defending in a few hours. Um, First, I'd like to thank Professor Ogbole for the invitation. It's a privilege to be part of Neuroradiology Nigeria's monthly symposium. So thank you for this opportunity. I had the date for yesterday and I switched it. Here's the outline of my session. Going to be talking about fingerprinting, mostly introducing what it means, why is it relevant, and show you some experiences from our multi-site study in terms of how repeatable and reliable it is. Then switch gears a little bit, show a method that we developed in the lab called tailored MRF, and some of its benefits from simulations all the way to imaging pediatric patients with brain tumors of different kinds. We also are the first ones to demonstrate MR thermometry using fingerprinting. So I'll just talk briefly about that and show you some ex vivo results on DBS lead heating. We've also developed an open source package for those of other people who want to actually reproduce some of the fingerprinting in a vendor agnostic way. I'll be brief about that and mostly tailor that with the amount of time we have. And finally, conclude and summarize these different topics that I'll be covering. Magnetic resonance fingerprinting came about in about 2012, 13, and it kind of advances this idea of qualitative imaging. And I'm speaking to the choir here, but radiologists like yourselves are used to reading weighted images, but the acquisition of some of these sequences takes long, and each contrast typically takes one pulse sequence. Um, on the other hand, quantitative imaging has been shown to improve diagnostic or prognostic value, and it kind of helps choose and monitor therapeutic efficacy. As an example, if qualitative imaging is analogous to saying that a car is going fast, quantitative imaging is saying that the car is going at 85 kilometers per hour. The limitation, however, is there needs to be significant training to investigate the data, and it usually takes longer than qualitative imaging, which in itself is slower compared to other imaging modalities, whole body imaging modalities like computed tomography and PET. There is this new realm of synthetic images. We've always used them for simulations, but now they've been looked at closer for um, translational and research use, which is, can you generate multiple weighted images using the MR physics that we really understand? And on the image on the right, if you see my mouse cursor, you can see if you actually generate certain parametric maps, like here, you can then use MR signal equations to generate a whole bunch of contrast, MR contrast, but these are synthetic. But they usually tend to be poor image quality. What I mean by that is effects of flow, some of the effects of diffusion show up as artifacts. Then you have the issue of partial volume because at the MR resolution, each voxel comprises of multiple types of brain tissue, like we all understand and know. So there are these limitations with that. The use cases for using quantitative and qualitative imaging exist in certain pathologies like brain tumors, multiple sclerosis, where the protocols kind of demand mostly qualitative imaging, but would also like to have access to certain quantitative measures such as a T2 map, for instance, or an ADC map. Um, in some cases, even an FA map. So there are these use cases where you need both. What fingerprinting does is it kind of bridges the gap by allowing access to multiple tissue parametric maps like T1, T2, ADC, and the like simultaneously. So you do one sequence, you get more juice out of it. So you squeeze the lemons more to kind of make different lemonades. Just to stay with the analogy, it does accelerate quantitative MRI because you use the reconstruction method in a way that is not normal but more based on pattern recognition. It suppresses some of the measurement errors. When I say measurement errors, I mean inhomogeneity in magnetic field of either B0 or B1, also motion to some extent. It does give you a lot of data in a very short time. So it gives you about 1,000 images of one slice in about 12 seconds. So it's a high velocity, high volume data. But at the same time, the use is not straightforward because it does not employ the widely used trajectories. It depends on simulations, reconstruction, quantitation, and repeatability. So it needs rigorous validation. Um, the idea in general is we've been thinking about MRI method development in standalone buckets of hardware, pulse sequence, image reconstruction, image processing, and parametric mapping if you need a parameter like T1 and T2. The fingerprinting kind of combines all of this into a monolith. Now you can add in the spice of the recent advances in deep learning, and then it becomes circular from going to be a unidirectional. But the challenge with that is it reintroduces system errors, meaning because you train with some known data, you're putting in the measurement errors that you had before. Um, Here is a one slide overview, and I'm going to probably explain this in another slide as well to get an intuitive way understanding of how fingerprinting works. On the top, you have the acquisition where you acquire 1,000 images, but you also at the bottom hand you simulate how it should work out to be. You acquire them with a bunch of random repetition times and flip angles, and you try to match what you acquired with what you simulated, and whenever that matches you get those matches tell you the values of your parametric maps, either T1 or T2, for example. Here's a visual representation of what actually happens. I think this is probably going to add more context. You acquire a bunch of 1,000 images, and you acquire each image with a different flip angle and a different TR. You pick a voxel of your choice, and it produces a signal intensity over those signal intensity profile over those 1,000 images. And then you go and you match it with your dictionary that you've already generated based on simulation. The entry that matches, the key to that would be a T1, T2, and of course, as you can imagine, you can have more parameters such as flow, ADC, um, even pH, and things like that. So that is or CEST imaging in general, but that dictionary matching, and that's the reason why it's called fingerprinting, because you are matching the voxel intensities over these 1,000 images or n number of images to a fingerprint that you already have created in your dictionary or your database. Now, uh, when we started our journey, we did some multi-site studies, and the goal of this study was to see if on one vendor, if we had two field strengths and three different sites, would we be able to reproduce the T1s and T2s mapped based on fingerprinting? We had three sites. One was Memorial Sloan Kettering, which actually headed this study. I was at Columbia at the time, and the third one was at Pisa. So we acquired 30 data sets of what is now known as the ISMRM NIST phantom, which I'll show you quickly, and then with temperature measurements. And then we looked at vendor supplied sequences as well as the NIST phantom values. We were mostly looking at the coefficient of variation to see to understand variability between centers. So these are the protocols for the gold standard. It takes about 40 minutes for the T1, and for the T2 it takes about 2.5 hours to characterize these. Our Center 2, which is Columbia, produced the gold standard T1 and T2 measurements, mostly based on our existing expertise among the three centers for physics. Uh, the acquisition parameters are on the left. It takes about 6 minutes to acquire 20 slices, 5 thickness. Um, Center 2, we had the 3T. So, but this has been demonstrated the 1.5T and 3T in MSK shows MSKCC or Memorial Sloan Kettering Cancer Center had both systems that they used. Here's the phantom that I was talking about. This comes from the ISMRM NIST community, which has these three layers of three arrays of T1, T2, and the proton density with very specific known values and very small standard deviations. Um, so we use this phantom for our study, and here's um, some of the outcomes of repeatability. What you're trying to see on the left in this very densely packed slide is um, one is the coefficient of variation, which you can actually see on both. On the left hand side, you see the plot of the T1 and T2 over days for the Phantom for 14 different spheres that the Phantom has. And you can see that they're pretty consistent. For the center that I was actually responsible for, you can see the coefficient of variation is the least. That actually tells you coefficient of variation is defined by standard deviation to the mean, shows you that lesser the better, and you can see that we have the least. In general, our MRF produce the smallest values for coefficient of variation. Also, relative correlation was estimated to just see the differences between two longitudinal measurements with a 95% confidence interval. And you can see that for the three sites, ours was the best with 95% confidence as well. In terms of accuracy, where we are looking at an R squared value in terms of the plot, you can see that they're pretty linear across the three sites and two field strengths, providing a bound of 95%. When you did the Bland-Altman plots, you can see that all the spheres are within the 95% confidence interval. So that kind of gave us the confidence that this method was repeatable across sites and two field strengths. With that, I'd like to get to the second topic, which is tailored magnetic resonance fingerprinting. Details of this can be found in the medical physics article, and I'm not sure whether I showed this, but there's another medical physics. Oh, here. The other medical physics article, which captures the multi-site studies, is in that reference. Okay. So I apologize for the back and forth on those slides. So if we revisit the synthetic MRI picture, um, again, speaking to the core, you radiologists generally work with contrast images. So to have these synthetic images is a little bit of tricky situation for people to believe. The synthetic images are not the parametric maps, but more the qualitative images that are generated on the right side here. And these suffer from the artifacts that I showed. So the general idea that we had at the time was if there is a single sequence that can actually uh, generate both qualitative and quantitative, but the qualitative not synthetic, but natural contrast or non-synthetic contrast simultaneously, that would be something that would be useful in clinic because it would save time for generating this quantitative maps, which are useful, but at the same time be able to still deliver the qualitative images that are the workhorse and the bread and butter uh, acquisitions that you need anyway. So the integration or the combining of these two into one sequence was the goal. Um, so we started out by looking, and this is a little bit of a physics slide. I'm happy to revisit this later. I know I'm talking to radiologists mostly. Is when you have a random set of flip angles, like you can see with the dotted lines, your magnetization keeps going up and down. But if you did like a smooth variation of this, like we propose in our method, then you will see that these magnetization values go either monotonically increase or decrease, or they're relatively stable. So the top panel shows the simulations, and the bottom panel shows the data actually acquired from a healthy volunteer. Um, what this does is basically it kind of gives you relatively slowly varying magnetization. Then you can actually perform what is in a sliding window, where you can collect data from the relatively flat blocks like that, and then be able to use that for generating natural or non-synthetic images. So our pipeline comprise not just of qualitative reconstruction, but also quantitative reconstruction. So first I'll talk to you about qualitative reconstruction, show you some images. The idea was to get the raw data, and then you select the time points based on the curve that I showed you, and perform sliding window reconstruction and generate these different images like the ones that, and these are all representative images. We'll show you also a repeatability study. And one of the other things that we were also able to manage is to look at water and fat. This is not directly clinically meaningful in the context of brain, but we did have motivations to use this to correct for some of the fat saturation issues that we were seeing in some of the other sequences. So here is a representation of a single volunteer still, and looking at three different contrasts of T2, T1 flare, and T1 weighted, all acquired simultaneously from one sequence, about 5.5 minutes. And you can see that we can vary the window size, which is 6 here. And you can choose from 6 contrasts, saying, hey, I'm a radiologist who I like a T of 80 milliseconds, but maybe there is another colleague who likes more 100 milliseconds. So you actually have that variable um, effect of contrast that you can actually get from the sliding window that I'm showing you here, where the contrast slot changes subtly over the window size. But the window size also adds reconstruction time. Um, but now it's not much of an issue with the compute that we have. We also did denoise these images um, using our own method called the native noise denoising, which basically gets noise patches from the images themselves, and then eventually uses them to denoise. We train on the Human Connectome project. For further details, you can look at some of my work from ISMRM in 2021, but I'm more than happy to talk about it in detail as well um, in the Q&A. So we also compared our denoising. The motivation for denoising was because you're acquiring data at such a rapid pace, your signal to noise gets a hit. So we were actually trying to compare. On the left side, you see the training, where you see the target SNR from the Human Connectome. This is the noisy images that we have simulated. And then you see the denoised image, which is very similar to the target image. On the right hand side, you see a real data set of T1 weighted data, where you can see the noisy image that we've picked out relative to the others. If you apply a state-of-the-art existing method called the gradient anisotropy diffusion method, you see the blurriness in these images. But when you actually apply the native noise denoising, it retains the structure, but you don't see the denoising level as much as the GAD filter. So we ended up combining the two to balance between information retainment and smoothness of the image. Um, Post denoising, here is another representative volunteer data where we're comparing the vendor supplied. So these are images directly from the GE. The synthetic images that you get with the flow artifacts, like we were talking about, and our method of the TMRF natural. Of course, the synthetic images cannot give you water and fat themselves, but we do. But ours suffers from the flow artifact when we do water and fat. But what we also want to do is to benchmark items from the first column and the third column to see how quickly how close we are. So our hypothesis is that the TMRF natural is closer to the gold standard than the MRF synthetic. So I'm talking mostly qualitative. Of course, doing or acquiring quantitative imaging will add more time here to the gold standard. And we acquired all of this for 5 minutes, slice thickness 5 mm and 20 slices. Now, when you look at the zoomed images to see, you can actually observe the partial voluming artifact as well in the synthetic MRF generated images where you see this pixelation. But here you see a smoother contrast, not as smooth as the gold standard, but this is naturally acquired. So you see the SNR dip a little bit, but it's definitely not patchy because you're not fitting one voxel to one value of T1 or T2. Similarly, you can see some of these items here in the T2 weighted image as well. Now, on the quantitative side, where you want to acquire or generate the T1, T2 maps, we used a sliding, non-sliding window reconstruction, and then 89 points moving average filter, which is similar to the sliding window, and then used reconstruction by Uri Cohen called uh, deep learning reconstruction of neural networks for fingerprinting or drone. And the reason we did that is when we did this with the conventional dictionary matching, with like the one that I showed you in an earlier slide, where we try to match the fingerprint, we were actually getting an underestimation. And if you use just a single point, you can see the artifacts of the spiral because our trajectory is a spiral show up. But when we did the drone, you can actually suppress these measurement errors and you see the recovery of the map quality. So that was one of the reasons we continued with the drone. Here's another representative image of the phantom when we looked at all the different images that you get in 5 minutes at again 5 mm slice thickness. So this is for 20 slices. Here are some online reconstruction, meaning we actually integrated a method to the scanner as well. That means you can now use this as part of the GE scanner. There is some other work also in Mikai that we reported. Now that I've been showing you mostly a single volunteer representative volunteer data, the next step, of course, was to look at this in multiple healthy volunteers and multiple repeats as well. Again, it's all in this article, which you see at the bottom. Similar to our multi-site study, we also performed an in vitro on the ISMRM list phantom. On the in vivo, we had 10 subjects. We repeated each subject 5 times, and each repeat had to have 2 runs so that you could compute the SNR as a subtraction between two. So in all, it was about 100 data sets, which is 10 times 5 times 2. And you can see on the right, the different contrasts that we are looking at, and also the segmented mask using FSL. Oh, I take it back, using 3D Surfer. And on the bottom, you can see the SNR comparisons between the three methods of gold standard and synthetic MRF and TMRF. And you can see consistently that TMRF is in between the gold standard MRF as we predicted. And the benefit of the TMRF compared to the gold standard is in the same time you also get T1T2 maps, and all of this just takes 5 minutes. Quantitative imaging in vitro is similar performance to the MR fingerprinting, but given that we haven't had as much randomness as in the original Jiang paper, you can start seeing that for smaller T2 values, which are about 20 milliseconds or lesser, which are more relevant in musculoskeletal imaging applications rather than, excuse me, neurological applications, you see higher coefficient of variation. And we did try to figure out why that is, and I'm going to get to that as well in a minute. The other observation is with the blind Altman, you can see now, earlier we did not have any point outside the confidence interval. Now we have one, but that's again something that we had for over a period of time, multiple repeats. So we started delving into why we were seeing this higher coefficient of variation in the smaller values. Turns out that the B1 or the radio frequency field at 3 Tesla is inhomogeneous, and when we prescribe a flip angle of 30, we end up getting more at the center, almost by 2 degrees, that you can see on the bottom right. We also observed these blips were because of temperature, that whenever there was an increase in temperature, you would see the increase in T1 and T2. That is validated by our knowledge of MR physics that T1 is correlated with temperature. I'll pick up on this again when we get to the other part of the talk, where we exploit this to introduce for the first time uh, MR thermometry using fingerprinting. Now, on the quantitative imaging, I showed you qualitative imaging on the repeatability side here, and the quantitation across those volunteers and subjects here. Um, you can actually see the quantitative imaging here, uh, which is on the T1 and T2 for a particular volunteer. You can see the 5 repeats. And you can see some changes in motion, but more or less you can see that the maps in the anatomy are highly repeatable with the T1 T2 maps. The statistical analysis involved computing the intra-class correlation coefficient, and what you can see is, and the gradings are on the right. You can pretty much see excellent correlations for white matter, gray matter, relaxation rates, and when it comes to the mean signal intensities as well. When we get to the SNR, it actually dips significantly, especially for white matter, and we attribute that to the interscan variation because our SNR method required 2 repeats or 2 consecutive scans to compute. And you can see the interscan variation, and that's the reason we attribute the reduction in SNR. The other thing is also our T2 weighted scans actually had significant, if you can observe here, has significant lower values for white matter. So it's almost like acquiring the data at 110 milliseconds rather than mostly about 80, 90. So those are the two reasons that we attributed for those values in the interclass correlation coefficients. And finally, we want to do this in brain tumors after doing this over 10 volunteers and 100 data sets. Um, and this is still an ongoing study. Our preliminary report is both at ISMRM and now also in the Journal of Clinical Imaging. So we scanned 5 patients so far, and you can look at the different kinds of brain tumors that you're seeing in different grades, different kinds, and also different tumor locations. Um, and we did this, I think, at the 2 mm slice thickness, and you can see the description of the therapy that's happened before, mostly surgery. And when we look at 3 mm slice thickness, I misspoke, thinking it's 2 mm. It's 3 mm slice thickness. When you look at the qualitative data of the 5 volunteers and across the 3 contrasts, plus the one that our radiologist really wanted to look at was T2. So that's our focus, and you can see the gold standard T2 and our T2 weighting, and you can actually see more like a still kind of effect with the suppression of the fat. And you can see also the reduction in the image quality between these two. We did quantify the tumors on the T1 and T2 maps, which is what the radiologist really wanted from this scan. And you can see the idea also, before I step, the idea also was, the main question that we were trying to get to was, in those pediatric patients that might not be able to hold themselves during the gold standard T2, which almost takes about 5 minutes, the idea was to use this also for the T2 use from the TMRF, but in all other patients to use it mostly for the T1, T2 maps. So, and this kind of had an impact on the number of the idea, or the, if I take a couple of steps back, the idea was to help avoid the use of anesthesia in these pediatric tumor patients, so that we could, with this one scan, be able to get both T1, T2 maps and T2 and T1 flare in contrast. Um, So with this, you can actually see the markings of the radiologist on these maps with the tumor and relative site for a normal tissue. This is all marked by the radiologist and not us. So we've basically gone with what the radiologist felt was right. Um, the couple of points we want to make. One is with the difference in T1s and T2s between healthy tissue and the residual tumor. Um, and you can see that in most patients, these are significant. Um, and that's kind of validating something that's prior knowledge. On the second one is the contrast that we wanted to see in those places between the gold standard or GE or vendor supply T2 weighted and the TMRF delivered T2 weighted. You can also see that there are similar trends between the two across the 5 patients that we've done so far. Finally, our observation on the change in T1 due to temperature, which has been known for a very long time, led us to looking at the use of fingerprinting in the context of DBS lead heating. And more details are in this publication in Physics and Medicine Biology. Going back to what we saw based on temperature and the temperature on those days. We knew this from a very long time, but we got this from fingerprinting, and that was our new contribution. Um, One area that we've really looked at is the use of deep brain stimulation leads. Again, I don't want to preach this to the choir here, but the idea is given that the DBS leads have now been extensively used in the treatment of neuropsychiatric illnesses, as well as other illnesses such as epilepsy and mood disorders and depression and the like. It is important to do these scans both safely and efficiently, um, which translates to an MRI protocol that induces minimum tissue heating. And also, you can use a temperature scout every now and then to make sure that you're not going beyond set limits. Current limits mostly based on how much power you put in, but having a real-time temperature map is where we want to go towards. The state of the art right now is called as proton resonance frequency shift, which requires kind of two scans. So that makes it both sensitive to intra and interscan motions. It also requires a separate off resonance map, and it's sensitive to field inhomogeneities. On the other hand, we require only one scan. It is better tolerant towards motion, and it generates its own B0 map. And like I'm going to show you, we need to improve on that map. But it does not suffer from the issue of complex coil combination, which basically means you could mess this whole thing in reconstruction that you probably see in a Dixon method when you see water and fat flip. Um, so we did some ex vivo experiments with bovine muscle, um, and you can actually see the three tissues. We used fluoroptic temperature probes as gold standard to measure these temperature measurements. In the middle is a water bottle at room temperature. On the top is cold muscle, and on the right is a microwaved um, piece of steak, basically bovine muscle. And you can see the color change because of the loss of water. And when we imaged this, we wanted to calibrate the T1 relationship with temperature as well. And you can see that goes by, and you can see those curves being fitted. So as T1 increases, so does temperature. We actually did a heating experiment where we heated these again, water bottle and muscle, and then cold muscle, and this is normal room temperature, where we started with the turbospin echo sequence, which started heating. So this is the one where you have the DBS lead in now. And as you can see, the one with the DBS lead heats up over time. And as it heats up, you see that the T1s actually increased. Um, so this is a T1 converted to Celsius map. And you can see that that kind of heats up. We also drew ROIs close by, and you can see I'm going to talk about the ROIs in a bit. But this graph is actually showing you the comparison of fingerprinting estimated temperature versus a fluoroptic probe. The key difference is the fluoroptic probe is actually taped to the DBS lead, whereas this is actually a few away because of loss of signal due to the DBS lead. I'm sorry for this overlapping text. I did not see it this morning. Now I see it now. Um, we also generate a B0 map inherently from the fingerprinting. And when we actually include that B0 map to correct for our T1 values, it actually corrects. Again, I apologize for this. I don't know what's going on here right now. Um, but the T1 map actually improves with B0 correction, but the uh, B0 map itself is underestimating the gold standard B0 map. So we've also thought about incorporating vendor supplied B0 sequence data into our MRF simulations. We did do an ROI analysis to understand the effect of the signal loss near the lead. Um, and as you can imagine, as you go away from the lead, like let's say the red ROI, the temperatures significantly fall because, as I showed you in one of my earlier slides, in the motivational slide, that the temperature drastically falls as you go away from the lead. Um, so as you go 6 mm away, it's more or less a constant. But when you actually look at 1 mm away, which is the closest that we can get, um, you see that there is an increase in the temperature around the lead, which we've caused due to radio frequency heating because of playing a turbo spin echo sequence. This is a quick video of showing that we integrated the MR fingerprinting based thermometry also into the scanner. Not extremely relevant unless you intend to use this RTS site right now, but this is something that we've been able to do on the uh, scanner and integrate it as part of the workflow so that people don't have to use this outside. And the images should pop up anytime now. What you're seeing is for the Phantom, we're trying to generate a bunch of T1, T2 maps and off resonance map because the Phantom it's homogeneous and um, we basically offset the whole thing. But that's something that we've been able to do. So in summary, across all these slides, um, we've had multi-site, multi-field strength, which is highly repeatable. Um, we developed a tailored MRF and conducted a repeatability study going all the way from simulations, in vitro phantoms, healthy volunteers, and then 5 pediatric brain tumor patients. We have also demonstrated MR fingerprinting based thermometry and looking at ex vivo data so far. With that, I'd like to thank my postdoc Pavan Pujar and my PhD student Enlin Chan, who's going to graduate today, hopefully, and all the wonderful collaborators and readers from across the globe. And you can see some familiar faces from Nigeria as well. Um, and the funding agencies. There is a shout out for anybody who's working in the area of deep learning and low field, especially for a frontiers call on autonomous MRI and frontiers in neuroimaging. Um, okay, with that, I'm happy to take any questions. I did not show you the open source fingerprinting, which is more engineering, and I'm happy to talk about it and also point you to relevant GitHub websites and publications if anybody's interested on that. With that, I'll pause. Thank you all for your attention again and for this opportunity.